question pertains to the 2005 National Electrical Code, specifically Rule 250.119, which addresses the identification of equipment grounding conductors. The core inquiry is whether this rule prohibits the use of green or green with a yellow stripe to identify the grounding electrode conductor, often abbreviated as GEC. The answer to the question is no. Rule 250.119 primarily governs the identification of equipment grounding conductors, and it stipulates that these conductors shall be permitted to be bare, covered, or insulated. If individually covered or insulated, they must have a continuous outer finish that is either green or green with one or more yellow stripes. However, this requirement applies specifically to equipment grounding conductors, not necessarily to grounding electrode conductors. To fully understand this distinction, it's crucial to differentiate between equipment grounding conductors and grounding electrode conductors within an electrical system. An equipment grounding conductor, sometimes referred to as an EGC, is a conductor used to connect the non-current carrying metal parts of equipment to raceways and other enclosures to the system grounded conductor, the grounding electrode conductor, or both, at the service equipment or at the source of a separately derived system. Its primary purpose is to provide a low impedance path for fault current to return to the source, thereby facilitating the operation of overcurrent protective devices such as circuit breakers or fuses. A grounding electrode conductor, on the other hand, connects the service equipment of the separately derived system to a grounding electrode, such as a ground rod, a metal water pipe, or a concrete encased electrode. Its function is to establish a connection to the earth, providing a reference point for the electrical system and helping to stabilize voltage during normal operation and limit voltage rise during fault conditions. Now let's delve deeper into the specific requirements for grounding electrode conductors as they relate to identification. While Rule 250.119 mandates green or green with yellow stripe for insulated or covered equipment grounding conductors, the National Electrical Code does not impose the same color coding restriction on grounding electrode conductors. In fact, Rule 250.64 addresses the installation of grounding electrode conductors and provides some flexibility in terms of conductor material and protection. It doesn't explicitly require a specific color for the grounding electrode conductor. However, it's important to note that Rule 250.64b requires that grounding electrode conductors be securely fastened to the surface on which they are carried. This ensures that the conductor is mechanically protected and remains in reliable contact with the grounding electrode system. Furthermore, Rule 250.64e addresses the protection of grounding electrode conductors that are exposed to physical damage. In such cases, the conductor must be protected by a rigid metal conduit, intermediate metal conduit, rigid non-metallic conduit, electrical metallic tubing, or other approved means. Again, this rule focuses on physical protection rather than color identification. It's also crucial to consider the size and material requirements for grounding electrode conductors, which are outlined in Rule 250.66. The size of the grounding electrode conductor is typically based on the size of the service entrance conductors or the equivalent size for a separately derived system. The conductor can be made of copper, aluminum, or copper-clad aluminum, and it must be sized appropriately to safely carry any fault current that might flow through it. While the National Electrical Code does not mandate a specific color for grounding electrode conductors, some local jurisdictions or project specifications may have additional requirements. It's always advisable to consult with the local electrical inspector or the project engineer to ensure compliance with all applicable codes and standards. Moreover, it's considered good practice to label or tag the grounding electrode conductor at accessible locations to clearly identify its function. This can help prevent confusion during maintenance or troubleshooting activities. The labeling can be done using approved tags, marking tape, or other permanent means of identification. In summary, Rule 250.119 of the National Electrical Code does not prohibit the use of green or green with a yellow stripe for grounding electrode conductors. This color coding requirement applies specifically to equipment grounding conductors. Grounding electrode conductors are subject to different requirements, primarily related to their size, material, protection, and secure connection to the grounding electrode system. While the National Electrical Code provides flexibility in terms of grounding electrode conductor color, it's essential to adhere to local codes, project specifications, and best practices to ensure a safe and compliant electrical installation. The grounding electrode conductor, crucial for electrical safety, connects the electrical system to the earth, providing a path for fault currents and stabilizing voltage. The National Electrical Code, or NEC, offers guidelines for its installation and material. Firstly, the material of the grounding electrode conductor is often copper, aluminum, or copper-clad aluminum. The selection depends on factors like corrosion resistance, conductivity, and cost. Copper is a popular choice due to its excellent conductivity and resistance to corrosion in many environments. Aluminum, while lighter and less expensive, needs careful installation to prevent corrosion, especially when in contact with dissimilar metals. Copper-clad aluminum offers a compromise, combining the conductivity of copper with the weight and cost advantages of aluminum. Secondly, the size of the grounding electrode conductor is determined by Rule 250.66 of the NEC. This rule links the conductor size to the size of the service entrance conductors. For instance, if the service entrance conductors have 2/0 American wire gauge or ORG copper, the grounding electrode conductor must be at least 6 AWG copper. The NEC provides tables to guide this selection, ensuring the grounding electrode conductor can safely handle potential fault currents. Thirdly, protection of the grounding electrode conductor is addressed in Rule 250.64. The conductor must be securely fastened to the surface it runs along and protected from physical damage. This can be achieved using conduit such as rigid metal conduit, or RMC, or rigid non-metallic conduit, or PVC. The choice depends on the environment. RMC offers robust protection against physical damage and corrosion, while PVC is suitable for corrosive environments but less resistant to physical impact. Fourthly, the grounding electrode system to which the grounding electrode conductor connects can consist of several elements. These include ground rods, metal water pipes, and concrete encased electrodes, also known as UFA-grounds. Ground rods are typically copper or copper-clad steel and must be at least 8 feet long. Metal water pipes, if used as grounding electrodes, must have continuous metallic contact with the earth. Concrete encased electrodes involve a length of bare copper conductor encased within a concrete foundation. Fifthly, the NEC specifies how the grounding electrode conductor must be connected to the grounding electrode. Connections must be made using listed connectors or by exothermic welding, also known as CAD welding. Listed connectors are specifically designed and tested for grounding applications, ensuring a reliable and durable connection. Exothermic welding creates a permanent molecular bond between the grounding electrode conductor and the grounding electrode, offering superior corrosion resistance and conductivity. Sixthly, the routing of the grounding electrode conductor is also important. It should be run as directly as possible, avoiding sharp bends or unnecessary splices. Bends can increase impedance, hindering the flow of fault current. Splices, while sometimes necessary, should be kept to a minimum and made using listed connectors or exothermic welding. Seventhly, when multiple grounding electrodes are present, they must be bonded together to form a grounding electrode system. This is achieved by connecting all electrodes with a bonding jumper, ensuring they are at the same potential. This reduces the risk of voltage differences between electrodes, improving the effectiveness of the grounding system. Eighthly, the NEC also addresses the use of aluminum or copper-clad aluminum grounding electrode conductors. These materials require careful installation to prevent corrosion, especially when in contact with dissimilar metals. Listed connectors suitable for aluminum or copper-clad aluminum must be used. An antioxidant compound should be applied to prevent oxidation. Ninthly, the grounding electrode conductor must be accessible for inspection and maintenance. This means it should not be concealed within walls or floors without provisions for access. Regular inspections can identify potential problems such as corrosion or loose connections, ensuring the grounding system remains effective. Tenthly, The NEC permits the use of the building steel as a grounding electrode, provided certain conditions are met. The steel structure must be effectively grounded and have continuous electrical contact with the earth. This can be a cost-effective option, but it requires careful engineering to ensure the steel structure meets the NEC requirements. Grounding electrode conductors serve a vital role in electrical safety by providing a low impedance path for fault currents to return to the source. This allows overcurrent protective devices, like circuit breakers and fuses, to quickly interrupt the circuit, preventing electrical shock and fire hazards. A properly installed grounding electrode conductor ensures that non-current carrying metal parts of equipment and enclosures are at or near earth potential. This minimizes the risk of electric shock if someone comes into contact with a faulty piece of equipment. By connecting the electrical system to the earth, the grounding electrode conductor also helps to stabilize voltage during normal operation. This reduces voltage fluctuations and improves the performance of sensitive electronic equipment. During lightning strikes or other transient voltage events, the grounding electrode conductor provides a path for surge currents to dissipate into the earth, protecting equipment from damage. Without a proper grounding system, electrical systems are vulnerable to a range of problems, including increased risk of electrical shock, fire hazards, equipment damage, and voltage instability. These problems can lead to costly repairs, downtime, and, most importantly, safety risks for people. Regularly inspecting and maintaining the grounding electrode conductor and the entire grounding system is essential to ensure its continued effectiveness. This includes checking for corrosion, loose connections, and physical damage. Any problems identified should be promptly addressed to maintain the integrity of the grounding system. The NEC is updated every 3 years to reflect changes in technology and best practices. Staying informed about the latest requirements for grounding electrode conductors is crucial for electrical contractors, engineers, and inspectors. These updates ensure that electrical systems are installed and maintained in accordance with the highest safety standards. Grounding electrode conductors are available in various sizes and materials to meet the specific requirements of different electrical systems. Selecting the right conductor for the application is essential for ensuring a safe and reliable installation. Considerations include the size of the service entrance conductors, the type of grounding electrode, and the environmental conditions. Proper installation techniques are crucial for ensuring the effectiveness of the grounding electrode conductor. This includes making secure connections, protecting the conductor from physical damage, and routing it as directly as possible. Following industry best practices and adhering to the NEC requirements will help ensure a safe and compliant installation. Grounding electrode conductors play a fundamental role in electrical safety and system performance. Understanding their purpose, materials, sizing, and installation requirements is essential for anyone involved in electrical work. By following the guidelines outlined in the NEC and adhering to best practices, you can help ensure a safe and reliable electrical system. Rule 250.119 focuses on the identification of equipment grounding conductors, requiring them to be green or green with yellow stripes. However, this rule doesn't dictate the color for grounding electrode conductors. The grounding electrode conductor connects the electrical system to the earth, while the equipment grounding conductor connects non-current carrying metal parts of equipment to the system ground. While green or green with yellow stripes is standard for equipment grounding conductors, grounding electrode conductors have more flexibility in color. It's crucial to differentiate between these two types of conductors when installing or inspecting electrical systems. Local codes and project specifications might have additional requirements for grounding electrode conductors. Always consult with local authorities and project engineers to ensure compliance. While the NEC doesn't mandate a specific color, good practice suggests labeling or tagging the grounding electrode conductor for easy identification. This helps prevent confusion during maintenance or troubleshooting. Proper grounding is essential for electrical safety, reducing the risk of shock and fire. Understanding the different types of grounding conductors and their specific requirements is crucial for ensuring a safe and compliant electrical installation. Staying updated with the latest NEC revisions ensures that electrical systems meet current safety standards. The grounding electrode conductor is a critical component of the electrical system, providing a low impedance path for fault currents. This allows overcurrent protective devices to quickly interrupt the circuit, preventing hazards. Regularly inspect grounding electrode conductors for damage, corrosion, or loose connections. Address any issues promptly to maintain the integrity of the grounding system. Proper grounding also helps stabilize voltage and protect equipment from surges. A well-grounded system improves the overall performance and reliability of electrical equipment. Grounding electrode conductors come in various materials and sizes to suit different applications. Select the appropriate conductor based on the specific requirements of the electrical system. The NEC provides detailed guidelines for sizing grounding electrode conductors based on the size of the service entrance conductors. Adhering to these guidelines ensures that the grounding conductor can handle potential fault currents. Proper installation techniques are essential for ensuring the effectiveness of the grounding electrode conductor. This includes making secure connections and protecting the conductor from physical damage.